for this course is to create a complete 8-bit working computer using simple transistors. Everything in the digital world is created using transistors, and the only thing that you need to know about them is that transistors are simple switches. We have two types of transistors, NMOS and PMOS. Each one of them has three terminals: gate, drain, and source. I of G, or the current through gate, is always equal to 0. Actually, the only thing that you need to know is this: if we apply the high voltage to the gate, the high voltage of the circuit to this terminal, to the gate, then the transistor would be on, and we say the transistor is acting as a short circuit. It just connects the drain and source to each other, so we say V of D is equal to V of S. On the other hand, if the voltage applied to the gate is at the low voltage of the circuit, then the transistor would be off. We say it is acting as a open circuit. This would be V of D and this would be V of S. They are just separated out of each other. PMOS is the opposite of the NMOS. If V of gate is equal to the low voltage, then we say transistor is on. V of S is equal to V of D. And if V of gate is equal to the high voltage, we say the transistor is off. So V of S and V of D, or drain and source, are separated from each other. You see, it's just as simple as that. It's a simple switch. From now on, for more simple, to simplify it further, instead of high, we say 1, and instead of low voltage, we say 0. So just know this: for an NMOS, if V of gate is equal to 1, the transistor is on, meaning V of D is equal to V of S. And if it is 0, then transistor is off. They are just separated. For the PMOS, it's just the opposite of that. Knowing that, let's create our very first circuit. This is our circuit which we have created using 4 transistors, 2 PMOSes and 2 NMOS. You see, when the arrow is towards the inside, we say it is a PMOS, like this. So let's see how this circuit works. If we have 2 inputs applying to here, we have 4 different combinations for these 2 inputs, right? We have A and B. So we either have 0, 0 for both of them. We have 0, 1, 1, 0, or 1, 1. You know that 1 and 0 are the high and low voltage, right? We are just simplifying the circuit. So we have 4 different combinations that we could apply to the input to see the behavior of the output. The output is this one. The only wire, or the only place that we are interested in its voltage level differences based on the applying voltage to the input is this wire. That's why I call this out and these 2 inputs. First case, let's say that we applied the low voltage, or 0, to both A and B to see the behavior of the circuit. So if we have 0, this 0 is going through this wire, so we have a 0 on the M2 PMOS, right? Also, we have the same thing for the B, which goes through this wire directly to the gate of M1. In here, we saw if we apply 0 to the PMOS would be on, acting as a short circuit. Therefore, this M2 would connect the high, this one to this one, right? It is just would be on. Therefore, the VDD would come here. We would have a 1. High voltage is VDD, that we are calling it a 1, right? So if we applied 0 to the gates of these PMOSes, the PMOS would be on, acting as a short circuit. So we have VDD, or 1, on this wire on the out. And actually, we don't need to check any other value, because only this PMOS, the M2 PMOS, is causing the VDD to go to the output, or 1 on the output. So we say if A and B are 0, 0, then the output is equal to 1. Second case is when we have 0 and 1. But we already checked that if only A is equal to 0, the output would be equal to 1. So 0, 1, we also have the out equal to 1. Third case, let me change the color. Third case is when B is equal to 0 and A is 1. 1 here and 0 here. So if you have 0 for B, this 0 would go through this wire to the gate of M1. We have 0 here, right? It is a PMOS. It just connects this VDD. In the M1 would turn on, connects this wire, the source of this transistor, to its drain, and its drain happens to be the out wire. Therefore, it would have VDD, or high voltage, or 1 on this wire. So we say 1, 0 also produces 1. So 3 cases, all of them are equal to 1. Let's check the last combination, which is 1 1. Let me just change the color. So if we have 1 1 on both of the wires, well, we have 1 here. This one goes through this wire to the M2. Also B is 1, so through this wire we have 1 on the gate of the M1. But we saw that 1 causes the PMOS to act as a open circuit, right? So drain and source of this would be just disconnected to each other. If I want to simplify the circuit more to the M1 and M2, I would have something like this. So this would be the M2 transistor because it is equal to because it is off, and this would be the M1. So I also have these two transistors which we haven't checked yet. So this is VDD, this is VDD, because they are just disconnected from the out wire. They wouldn't have any effect on that. But we have these two NMOSs which are just connected to A and B, right? This A comes through this wire to the gate of M3, and B comes through this wire to the gate of M4. Both of them are currently 1. So if A is equal to 1, as we saw previously, 1 causes, or high voltage causes, the NMOS transistor to be turned on and acting as a short circuit. So if M3, this transistor, is on, then it would be a short circuit, right? And B is also 1, and it is the gate of the M4, which happens to be another NMOS. So this is also a short circuit, and as you see, they go toward the ground. So this here would be the ground, or lowest voltage, or 0. As you see, out is connected to the ground directly through M3 and M4 wire, so out is equal to 0. So as we saw, the last case causes the out to be equal to 0. So we created a circuit that has two inputs, A and B, and one output, which is out. We say the circuit acts like this, that the output of the circuit is equal to 0 only when both inputs are equal to 1. Otherwise, the out is equal to 1. We could just call this circuit a NAND gate, as it is called out in the electronics word. And they say that everything in the digital world could be created using this NAND gate, but we are not going to abstract this circuit and create the computer using NAND gates. We are going to only work with the simple transistor and always see the flow of the current and the voltage levels of different wires at the transistor level, and not using any kind of abstractions. I also wanted to create another circuit, and it's the same thing, only the inputs I have connected them to each other. Therefore, we only have one input, or A, right? So if we have one input and we are getting the out from the same wire, we say, well, the input could only be 0 or 1, right? This is A and this is out. We want to see how out changes with the changes in the inputs, which is A. So first, let's see what would happen to out if A is equal to 0. So if you have 0 here, let me change the color. If you have 0 here, this 0 goes to the M2, and also it is connected to this gate. This is also equal to 0. 0 causes the PMOS to be turned on, therefore out would be connected. Well, both this VDD would come to the out wire, and out would be equal to VDD, or 1. So when A is equal to 0, out is equal to 1. The other case is when A is equal to 1. If A is equal to 1, we have 1 at the gates of M2, M1, M3, and M4, right? The last case, when we applied 0, 0 is also at the gates of M3 and M4, but they are off and they wouldn't have any effect on the out voltage level. But right now, we have 1. This 1 causes M2 and M1 to be turned off, and only M3 and M4, which are NMOSs, would be turned on, acting as the short circuit. So we say out is equal to would go to the ground using the M3 and M4 path, and out would be equal to 0. So when we gave A the input 0, out became 1, and when we gave it 1, out became 0. We could just create another abstraction and say 1 input, 1 output. The output would always be the complement of the input. This is usually called a NOT gate, and in different softwares they show it using this symbol. As I said, these were to just I guess give you an explanation how you could follow through the voltage level of different wires based on the changes of the inputs. In the next lecture, we are going to create this circuit to see how this circuit would act as a 1-bit memory by just trying to find out the voltage levels of the different wires, the out 1 and out 2, based on the inputs of I and S.